Let us try to understand how to build agentic AI applications or building AI agents. We are going to use OpenAI Agent SDK. You can think of it as a lightweight framework that gives us the right primitives like agents, tools, handoffs, hooks, guardrails, context, and an agent loop. Here is the mental model you will see in the code, like agent, runner, function tool, guardrails, hooks, hands off, context, and model setting. Let us set the flow, like how we will learn. So we are going to start with the smallest agent plus runner, just instructions plus model. Then we will add model setting to add the tuning parameter in the agent. Then we will plug in some hosted tools and the custom tool. And then we will introduce hands-off and on hands-off hooks. We will add guardrails. Then we will use the context and the memory for state across turns. And then we will encode the agent loop in instructions, drive it with a tiny controller. And finally, we will finish with the evaluation. This evaluation will help us to evaluate the agentic application or the solution which we are going to develop. All right, so let us begin coding. In this notebook, we will build up from the smallest possible agent to a multi-agent system with tools, handoffs, guardrails, hooks, and memory. Exactly the ingredients of a production-shaped agent. Every section is incremental. We will add one item at a time. So let's proceed. We installed the OpenAI Agent SDK and Python.env. The SDK gives us higher level primitives to build agent, runner, tools, hands-off, and etc. So we spend less time wiring and more time shipping. And .env lets us keep secrets out of the code. Once our libraries are installed, we will import the needed libraries to create the setup. We will read our API key from the environment and set the default client for the SDK. If you are using a local LLM or Azure later, then this is the block you would swap to point at your base URL and model. The rest of the notebook remains unchanged. Here we are using GPT-4o Mini from OpenAI. Now our setup is ready. Let us spin up our very first agent. Two imports, the agent and runner. So this agent block defines our first tiny agent. You give name to your agent. Now this is just hello agent. And then this is your instructions to this agent and the model this agent is supposed to use. So we gave the agent a name, a single sentence of instructions, and a model. Keep the instructions short and action oriented. We will add tools and guardrails later. Now here we run one turn. So input can be a string or a chat transcript. Here it is just a prompt like result.final.output is the agent's reply. Because runner.run is async, this works in the notebooks with await. So use runner.run underscore sync in a plain script. So let us run this. So here our agent responded. So the instruction given to this hello agent was, you are a helpful assistant, and the user input was write an article about AI agent in 5 lines, and this is the output generated by our tiny agent. Now to make the model predictable, there are different knobs available through model underscore setting. So this model underscore setting gives you different tuning parameters or different tuning knobs to set the model behavior. Now here we are going to use two such knobs. One is temperature and another one is max token. So here we are setting temperature as 0.2, which is more deterministic, and max token as 200 to keep the answers short. So again, this is our same hello agent where we are saying be concise and friendly. And then the question is, tell me about AI agent in one short paragraph with these model setting parameters. And now let us see the response. So here is the response of our agent. Now there are different knobs also available as part of model setting. So this piece of code tells you about all possible knobs which you can tune as part of model setting to optimize your agent behavior. All right, now tools. Tools are where the real work happens. Tools let agent take actions like fetching data, running code, calling external APIs, and even using a computer. Now, because we are using OpenAI Agent SDK, so there are three classes of tools in this OpenAI Agent SDK. The first one is hosted tools, another one is function tool, and the third one is agent as tools. So let us see each one of them. So the first one is hosted tools. OpenAI provides some hosted tools. These are the current hosted tool set from OpenAI. Of course, this list will keep on growing. So currently it supports web search tool, file search tool, computer tool, code interpreter tool, hosted MCP tool, image generation tool, and local cell tool. In our example, we are going to use one web search tool, which is the hosted tool from OpenAI. Now here, if you see the agent code, now to include the tool in your agent, here is the tool configuration. So you need to configure this tool parameter inside your agent and give the tool name in the list. Now here we are using the hosted tool. So this is how you provide the list of tool in your tools parameter. Now to use this tool, we need to import this tool from the agent library. And the rest of the configurations are the same. Now here, the name of our agent is web researcher, and the instructions are like you can browse the web when a question requires up to date info or citations. Use the web browser tool and include the source you used. Now let us run this. Now here, what is expected is that here the user question is, what is new in RAG evaluation in the last 3 months? And cite sources. So now for this user query or question, it is expected that this agent will do a web search using OpenAI web search tool, which is a hosted tool, and bring the response. Now, if you see the response generated by the model or the agent, now in the instruction, we have also mentioned that cite the sources. That means the URL. Now let us see the results. So now it is saying Amazon Bedrock enhanced RAG evaluation capabilities. So it has got this information. Now let us see the source from where it has got this information. It should tell the URL of. So this is okay. So this is the AWS Amazon website from where it has got that information. Similarly, for all other sources, it has also cited the source information, which is the corresponding URL. So this agent is also working as expected. Now, the hosted tool may not be enough and may not fulfill all your requirement, and therefore there is a function tools. Now, you can use any Python function as a tool. The agent SDK will set up the tool automatically for you. So the name of the tool will be the name of the Python function. For example, say here I have this function, which is time now, and the job of this function is to return the timestamp. So here is the function definition, says return current UTC time in ISO format. So the name of the tool, which is this time_now, will be the name of the Python function. Okay, so this is the name of the Python function, and that is going to be the name of the tool. And tool descriptions will be taken from the doc string. So the doc string, which is here, so this is the doc string. When you embed a string into this triple quote, it becomes the doc string. So tool description will be taken from the doc string of the function, because the LLM will refer this doc string to understand the function behavior or what this function is supposed to do. The schema for the function inputs is automatically created from the function's argument. Descriptions for each input are taken from the doc string of the function unless disabled. Agents become powerful when they can act. So let us explain a tiny Python function, time now. This decorator turns a plain Python function like this into an LLM callable tool. So this time now function because we have added this decorator, now become a callable tool. Now inside our agent, we need to include this tool through this tool parameter. So the tools considers a list of tool sets. So here we are just defining one tool and telling our agent that this is the tool available for you. So, and we are providing the instructions as if asked for a current time, call the time now tool once and answer briefly. Now, if somebody is asking what is the current time, then as per this agent definition, it should call this tool time now, execute this function, get the result, and then display the result to the user. Now let us run this piece of the code. So now it is saying the current time is 14:59 UTC on October 16, 2025. So this agent is able to call this time now tool and display the current time. Now the third class of tool in OpenAI Agent SDK is agents as tool. This allows you to convert an agent as tool. Now here, if you see, we have two agents. One is Spanish agent, where the instruction given to this Spanish agent is to translate the user's message to Spanish, return only the translated text. And then the second agent we have is French agent, where the instruction given is that translate the user's message to French, return only the translated text. So these are the two agents. Now we are defining a third agent, which is orchestrator agent. Now orchestrator agent will call the worker agent as tools. So these two agents, which are a worker agent, they will act as a tool for this orchestrator agent. Now the orchestrator agent, if you see the instruction, it says that you are a translation router, decide which language is requested and call the matching tool. To translate, call the tool with a single string argument named input equal to the user's message. After the tool finishes, return only the translated text. If the user asks for multiple languages, call multiple tools and label each result. In this orchestrator agent or routing agent, this is where now we are configuring our tools. Now, if you see here, this tools configuration, here we are using these agents, helper agents as tool. So Spanish underscore agent dot as tool and French underscore agent dot as tool. So these agents or the helper agents will be used as a tool in this orchestrator agent. For this user query, say hello, how are you in Spanish. This orchestrator agent or the router agent will call the Spanish agent as tool and get this job done. All right. Now there is something called control tool behavior. Stop on tool versus run LLM again. Now here what happens when you make a tool call, do we want the model to run again and synthesize a nice sentence, or do we want to stop immediately and return the tool's raw output as is as an output? So this is where the tool underscore use underscore behavior is used. Now the default is run tool result with LLM again. So if you do not set this parameter here, then the default behavior is that when the tool call is made and whatever response this tool returns, that response is sent to the LLM and then LLM synthesizes that result and then it generates the final outcome. But if you want that, if you want to send or present the tool output as is as a response of this agent, then what you can do, you can set this parameter as stop at tools. Now, when you set this parameter stop at tools, and then you provide the tool name, then what happens when for this user query, what is the time now? When this tool will be called, this time now tool will be called, and this time now tool will generate the response. It will return the timestamp. Then this agent will return the timestamp directly, and it will not send the timestamp to the LLM, and the LLM will not then further synthesize your response to make it more user friendly. So for example, let us run this agent, and if you see here, the output of this agent is just the timestamp, which is the output of this tool call. Imagine you have multiple agents and one routing agent. Now that routing agent routes the input or the requests to a right specialist. So if the user is speaking Spanish, hand off to the Spanish agent. If user is speaking English, then hand off to an English agent, something like that. So you can also say that this is kind of an intent routing or intent analyzer, and it analyzes the user intent based on the user query and does the routing accordingly. Now in the handoff example, we have multiple agents. So let us see how the handoff is implemented. So these are the two agents we have, Spanish and the English agent. And now see the handoff in the agent, in the router agent. So this is our router agent. Now here, so this is how you define handoffs. So you define a list and provide the list of agents to which this router agent will do handoffs. Now, if you see, we are calling this agent twice, one with Spanish query and another one is with English query, like hello, how are you? Now, let us run this. The input was hello, how are you? And this is the model response. Now, the first input was in Spanish, and therefore this router agent, because it was meant to do hands off to the corresponding agent. So for the Spanish query or for Spanish input, it handed over to the Spanish agent, and the Spanish agent produced this response. For English query, it has handed over the request to the English agent, and English agent produces this response. So this is how you implement handoffs in your agent. Now we understood handoff. Let us understand handoff hooks. Now handoff hooks is something through which you pass some preloaded context to the helper agent. So that means when a routing agent is routing an input request to helper agent, it can preload some context and pass on those preloaded context to the helper agent while handing over the input request. For example, here we define a shared context or the context which we will be preloading during the handoff. Now here, this is a lang context where we are saying the language, the greeting, and the style. And then we define the handoff hooks. So here we are defining two handoff hooks. One is for handoff Spanish, on handoff Spanish. That means when the router agent will hand off the user query to the Spanish agent, this on handoff Spanish will be called to prefill this lang context. And when routing agent is calling the English agent, then this on handoff English hook will be called to prefill the context. Now here in the main agent, which is here, you see we defined these hands off. So here, these are the two handoffs and the corresponding handoff hooks. So this is how you define the handoff hooks inside the handoff call. Rest all are same. So now here we are going to call. So we are instantiating our context. Then whenever we are making a call, this runner.run will make that call to the agent, and the agent will then call the main agent, or the router agent will call the corresponding helper agent and pass this context. So if you see the output for the Spanish agent, the first Spanish agent for hello, how are you? And these are the context which was passed. And similarly for the English agent, for the second query, hello, how are you? These were the context which were passed. Agents often need to return machine readable results or structured result, for example, JSON output. Now we lean on pydantic models for types. This is how you make LLM outputs concrete and testable. So here we are using Pydantic. Now, for example, you need to install and import the Pydantic and then import the Pydantic base model. Here you define a Pydantic base model class or your structure which you want your agent to return. And then in your agent, inside your agent, you just need to configure output underscore type parameter, and then you configure this with your typed object. In this case, it is plain. And here, then what happens, like when you run your agent, where name of this agent is planner and the instructions is like turn wake goes into a concise plan with 3 to 6 steps, and say the input is plan a 2-hour workshop on prompt engineering, then when this agent will generate the response, it will generate the response with title, steps, and confidence. Now let us run this. So now you see the response generated by this agent, planner agent, is having the title, then steps, and then it will also have the last one, which is the confidence score. So this is how you enforce your agent to generate structured output. Guardrails gives you policy and quality checks without writing a wrapper service. There are two types of guardrails: input guardrails. Another one is output guardrail. Now, if a guardrail trips, you can return a friendly error or a route to a human. So that is the behavior you can define when you are defining your guardrail. Now here, in our use case, we are defining one input guardrail and output guardrail. But let's try to understand the structure. Now here, this, so here we are defining again Pydantic class. It's a summary. This is where we're trying to fix the structure of the agent response. And then even before that, let us see, to implement this input and the output guardrail, you need to import this input guardrail and the output guardrail, then the guardrail function output from the agents. Okay, now this function runs before the model sees the user's message. Okay, so whenever the model sees the user message, because this input guardrail is configured in the agent. Now, if you come to the agent code here, you see the input guardrails and the output guardrails are configured. So how it works is that when agent sends the requests to the model, and then the model finds that this input guardrail and the output guardrail is configured, then the model will first execute this input guardrail, which is the block sensitive. Now, when it executes this block sensitive, it will check if the user input is having any keyword like password, credit card, and SSN, something like that. Now, if that happens in the input, then here we have defined that tripwire triggered as trip. Now, tripwire triggered as trip means block this turn. So when a tripwire is triggered, the SDK flags the turn. Now, typical app policies are refuse with a safe message or ask the user to rephrase or route to a human. So those are the three possible scenarios. The point is we stopped the model before it could produce unsafe output. That is the main objective. Now, output guardrail, it validates the model's structured answer. Okay, so this runs after the model, but before you accept the final answer. So when the model response is generated, model runs this output guardrail, and then if this output guardrail here, in this output guardrail, if the output is summary, the SDK parses the model output into a summary object. And then we enforce a simple requirement like at least 2 key points. So here, in the tripwise triggered, it is the condition is mentioned, right? The condition is like if the key points are less than 2, then this becomes a trigger point to highlight or call this output guardrail because the expectation was that at least 2 bullet points to be there in the output. That was the requirement. And if that requirement is not met, then the SDK should stop the output generation for the user or for the agent. Now let us run this. So here you see in the input, we are saying how to reset a password. Now, yeah, so now you see the input guardrail was called and it says that the guardrail input guardrail triggered tripwise. And that happened because the input was having a keyword password and this keyword was configured as part of the input guardrail. So this is how you implement input and the output guardrail inside your agent. In the agentic AI or in AI agents, there is something called hooks for observability. Now, what are hooks and why do we need them? So hooks are callbacks. The agent's SDK fires at important moments in the agent's lifecycle. For example, when a turn starts, when a tool is called, when the turn ends, etc. So at these important points, these callbacks are made. So these hooks let us observe what the agent is doing, like who ran it, which tools were used, how long it took, etc., without changing business logic. In production, these hooks feed logs, metrics, or the traces, so we can debug and measure our agent's performance and behavior. So let us do a quick walkthrough. We are importing this agent, the runner. These are our core SDK primitives for agents plus execution. But here we are importing agent hooks, which is a base class. We subclass to receive lifecycle events. Then the function tool, which is decorated to expose a Python function as a tool. And yeah, so here we subclass the agent hooks and implement the methods we care about. For example, we implement one method called onStart. So it fires at the beginning of a turn. Okay, so good place to record a timestamp, request trace ID or user ID, etc. And then the other hook we are defining is on tool start. Now on tool start fires before each tool invocation. So great for a tool audit trial. And the third one is on end. So this gets fired when the turn completes. So we can log the duration and the summary of the overall execution of the agent. All right. Now we have our tool as a Python function. Then in our agent, which is a toolie agent, and the instruction is if asked for the time, call time now once, and there we have the tool configuration, and then we decide or we configure our hooks, which is the log hooks. Now, when this agent will run for this input, what is the time now? Now, these log hooks here we have defined the hooks at on the start, on tool start, and on end. So at 3 places, these log hooks will be called and the logging will be done on the respective places. So let us run this and see the output. Now you see when the agent start, so the logging is done at the start where here hooks start and the agent name we were logging. And when the tool is being called, we are dumping the tool name. And then at the end, we are saying the hook ends. So here in the output, you see here, when the agent starts, the hooks is called and it is printing the agent name. And when the tool call was made, this hook is printing the or logging the tool name. And then when it ends, it is logging the end statement. And then this is the output of the agent. All right, this is how the hooks work for observability and the lifecycle logs for our agents. Now, this cell shows you the smallest possible way to give an agent a memory across turns. So we are building a memory demo agent, and here no database, no extra plumbing, just by passing the running transcript back to the agent each time we're just trying to demonstrate the how we manage the memory inside an agent or agentic workflow. So it's a plain agent with one job, which is remember facts the user states in this conversation and reuse them later. Okay, so it's a plain agent with one job, like remember and use facts. So there is no special memory module here. The memory comes from us consistently giving the model the full conversation so far. So now to do this memory management, we are declaring history list. So now here you see we are defining a helper function called turn, and in this helper function we are going to append the user's new message to history. Okay, and also the assistant message or the assistant response to the history list, and we print the reply here. Okay, so that is what this helper function will do. Now from the model perspective, every turn looks like a standard chat transcript, right, with all prior turns, because when we are going to call the model here, we are going to pass the history or the entire history. So therefore, from the model perspective, every turn looks like a standard chat transcript with all prior turns. So it can, pull earlier facts. And when you ask follow-up questions, then it may refer to the previous conversations and then provide you the corresponding response. Now, for example, here we are calling our this helper function, and first time we are saying my name is Priya and I live in Pune. Then asking what is my first name and which city do I live. Then because this agent is having this access to the history or historical conversation, then it may refer to this first conversation and then it can derive the name and then it can derive the city in the response. So let us run this. And then you see here, when the input was my name is Priya and I live in Pune, then the assistant is saying, got it, Priya, you live in Pune, how can I assist you today? And then the follow-up question is, what is my first name? Then the agent is saying your first name is Priya. And when again the next question is like, which city do I live in? Then the assistant is saying, or the agent is saying, you live in Pune. So this it was able to generate this response or these answers because it was having access to the memory or history. Now, there are a few important notes to tell you about this memory management. Now, this memory management which we have implemented, this is, ephemeral memory because if you restart the kernel or this colab, and then you create a new session, then the agent forgets the previous conversation. So therefore, you need to, create the persistent memory. Now, persisting the memory, it requires saving the history somewhere, durable and reloading. So you need to save it somewhere as a persistent storage, right? Now, another thing we need to note is that the bigger history grows, the more tokens you spend and the slower it gets. So in production, you will often summarize older terms into a compact working memory message and keep a structured context. So you can use the parentic model for key facts, for example, the user's first name and the user's city, something like that. And truncate or window the transcript to stay under token limits, because every model is having a max token limit, and therefore we cannot continuously keep growing the chat history. At some point in time, we need to do the chat history management. And then there are different options, like one is the summarization, and then one is like you remove the oldest one, something like that. So those optimizations we need to implement in the production grade system. All right.
This video is part of my course Mastering AI Agent using OpenAI Agent SDK, the course which I have published on Udemy. The link of that course is available in the description. So if you are interested, please follow the link and get your certification done.